Welcome to the second video on gas laws. So what I'm going to ask you to do here is I want you to pause and look at the graphs that you made from the lab and try to answer the following questions based on the data from the lab. So go ahead and pause now, answer the questions, and then resume when you're ready to be dazzled with brilliance. So I'm going to do this kind of stepwise. Here is what one of your graphs should have looked like. This is pressure versus temperature. Okay? So if you decrease the temperature of a gas, okay, so if we decrease the temperature of the gas, what happens to the pressure? Well, if temperature goes down, we can see that the pressure also goes down. All right? Now, what is the mathematical relationship between pressure and temperature? Okay? Now, we got to be a little careful here. Okay? Something that is directly proportional would go through the points 0, 0. That's not going to happen here, okay? So there's a scale issue. But we know that as temperature decreases, pressure decreases, or as temperature increases, pressure increases. So there must be a point where there is no pressure. Think about that. Okay, how could there be no pressure? Pressure, this could only happen if there are no collisions with the walls of the container. And that could only happen if the particles of the gas aren't moving. That's the only way that they won't collide with the walls of the container. Okay, we call the point where all motion stops absolute zero. Absolute zero. Okay. Okay, and scientists figured this out a while ago, and they invented a new temperature scale where the temperature and the pressure would be zero at the origin. Okay, and they called that scale the Kelvin scale. So in the Kelvin scale, there are some interesting features. So the first one is that absolute zero is set at 0 Kelvin. All right? And each increment is the same as the Celsius scale. Okay? So a change of 1 Kelvin would correspond to a change of 1 degree Celsius. Fair enough. And so I can give you some definitions here. 0 Kelvin happens at negative 273.15 degrees Celsius. That means that 0 degrees Celsius is 273.15 Kelvin. 1 degree Celsius is 274.15 Kelvin. So I want you to pause and see if you can figure out how to convert Celsius to Kelvin. What should be apparent is that all I'm doing is taking the degrees Celsius and adding 273.15. So to convert degrees Celsius to Kelvin, you take your degrees Celsius plus 273.15. Done. and you'll get your Kelvin. So if I take the above graph and I changed the scale of the temperature axis to, instead of being temperature in degrees Celsius, to temperature in Kelvin, what I get is a graph that looks like this, okay, where here are all my data points, and my temperatures are all up here, but look, it forecasts down to, it's not exactly the origin, but it's near the origin, and for us, that's pretty conclusive data that 0, 0 is the origin if you use the temperature scale, okay? So, let's continue and talk about, now we can go kind of back to the mathematical relationship. Now we can say that pressure and temperature in Kelvin are directly proportional, okay? So let's think about this in terms of what particles look like, all right? So we say that pressure is directly proportional to temperature. That's what this alpha sign means. It means directly proportional, right? So I have my particles of gas floating around in a syringe, okay? And the syringe is hooked up to a pressure probe, much like the lab that you did. And I heat the syringe, okay? Well, you should know that when you heat the gas particles, pause here and think about what happens. When you heat the gas particles, they're going to start moving faster. When they move faster, there are going to be more collisions with the walls. And each collision is going to have more force. So they're going to create a higher pressure. Okay, so as temperature increases, the pressure of the gas is also going to increase. So let's go take a look at our simulation that we were using yesterday. Okay, if I add a little bit of heat here, look at the particles go. They're starting to speed up. Now they're going crazy. They're going so fast. Okay, more particles bouncing off the walls. They're moving faster. They have more force. And you can see that the pressure also increased. Okay, just going to cool it back down to something reasonable. All right. So, what are we going to do with this? Okay? Anytime that you have a proportionality like this, you can turn that into an equality. Temperature, so pressure equals temperature times some constant, which for now we're going to call K. And you'll come to hate K in this class, and I'm sorry about that. But a lot of the constants that we'll use are K. All right. So if I solve for the constant here, pressure divided by temperature has to equal this constant K. Well, let's think about that. I have a gas that's trapped. All right? And this K has to be a constant, which means it has to be the same here as it is here. So the ratio of pressure to temperature always has to come out to the same number. So I can say that P1 over T1, so the pressure divided by the temperature in this first syringe before I heat is equal to K, which is equal to this P2 over T2. And, you know, if A equals B equals C, I can say that A equals C. So P1 divided by T1 equals P2 divided by T2. All right? This is called Gay-Lussac's law. All right? And it's one of the gas laws that we're going to use. So the next thing on the list is to try a sample problem. But that'll be on the next video.